All right, so we are going to work through some of the problems on our review sheet in this recording. Um, you can find your review sheet on Moodle in the exam review material section. It should match the one that we handed out in class, at least pretty closely. So we can look through, we'll kind of like just talk through how to go through these problems, what we should be thinking about when we see each of the problems. It's good that we're going to look at a lot of multiple choice questions because we could talk about how you can sort of help eliminate answers that don't make sense and maybe focus in more on answers that do make sense. But do keep in mind that the questions that you're seeing here, they are not exam questions. Um, you can feel, however, comfortable uh, about taking the exam if you can move through this review sheet and are confidently answering these questions correctly. Okay. A few good tips when you're using this review. You can take your review sheet. You can practice some of the problems with it on your own for sure. Always good idea to try some of these problems out on your own. When you get to a problem that you don't know how to do, you can like flag it and make sure that you look for that one in the video. And once you start watching the video, you kind of check off where your answers are right and wrong. Or you can compare your answers to the answer key, which is also a Moodle. So you can hone in specifically on the questions that you're not getting correct. But you do want to start working through why you're not getting some of these answers, focusing on the specific areas that you want to practice more with so that you can use the time you have before the exam to really, learn the material that you're still struggling with, practice a little more with the questions that are still giving you trouble. Okay. And this is a good review because it reminds you of the full scope of the things that are going to be on your next exam. I know that it's very easy to focus in on like the last thing that we've learned. And so we want to remember the entirety of what's in this unit. Okay. So I will share my screen so we can look at uh start looking at the questions. Our first question here uh is asking us which of the following indicates that a chemical change has occurred. So this is from the beginning of our chapter 7 discussion. When we talked about the signs that you would look for when you're trying to, observe a chemical change in a reaction. And if you look through all these choices, a color change occurring, that was definitely one of the things that we discussed. Heat is given off. Yep, that's definitely one of the signs that a chemical change has happened. A solid forms, that's definitely one of our indicators. A gas evolves. That word evolve means it's been given off as a result of the reaction. So, like if you see bubbling occurring when you mix two of your reagents together, that would be gas evolving in that situation. But that is also an indicator that chemical changes happen. So, in this case, all of these are correct. All right. Let's look at our next one. Oh, let's erase these check marks. So next question, the next two questions are balancing questions. Um, and so they're asking us for the coefficients that are needed to balance these equations. Okay, so we'll do both of these on the board so that we can talk out the steps. So remember our main rule when we're balancing chemical reactions is that we can change coefficients, which are the things that are in front of the compounds. So we can change those things. but we can't change subscripts. Okay, so these subscripts that are part of our chemical formulas, which we only have two of them here and here, those we cannot change as we're balancing. All right. So we're going to start off by making our little table that's going to help us keep track of how many of each atom that we have on each side. And we have aluminum, hydrogen, and chlorine on each side. So on our left side, we have one of everything. And on our right side, we've got one aluminum, we have three chlorines, and we have two hydrogens. Okay. Because the chlorine is part of a compound on both sides, I'm going to start by balancing my chlorine first because my hydrogen and my aluminum are by themselves. Okay, so I'll save those to the end. So to balance my chlorine, I'm going to need to multiply the compound that contains chlorine by 3 on both sides. Okay, so that multiplier that I used to make our number of chlorines the same, that multiplier is going to go in front of my compound that contains chlorine. It becomes the coefficient. Okay, and then that coefficient, it doesn't just apply to the chlorine, it also is going to apply to the hydrogen that's in that compound. All right. Now what happens here is I'm going to look at this. I've got 3 hydrogens and I've got 2 hydrogens, right? And I have to make those numbers the same. In order for me to make those numbers the same, I'm going to have to multiply my um, my hydrogen on the left side by 3. And I'm going to have to multiply my hydrogen on my, did I say the left side? I'm sorry, I'm going to have to multiply my hydrogen on the right side by 3 to get 6 hydrogens on the right side. And this hydrogen that's over here on the left, I'm going to have to make a little modification here, right? Because I have 3 hydrogens here, which a multiplier of 3 here, which gives me 3 hydrogens. But now I'm going to have to multiply that by 6 instead, so that I can have 6 hydrogens over here. And when I change the multiplier in front of my hydrogen, that means I'm going to be changing that coefficient that I've placed here, which is okay. You're allowed to change coefficients as you go. The part of the balancing is that sometimes you'll make a modification to a coefficient that you've already put down, that you've already locked into place. Until everything's balanced, no coefficient is safe. Okay. Now that I've changed the coefficient in front of my HCl, I've changed my multiplier for my hydrogens to 6, but I'm also going to change my multiplier in front of or for my chlorine to 6 as well. Okay. No problem there. But now I have a mismatched number of chlorines. Oh, let me just put this multiplier of 3 out in front here. So I come back to my chlorines that are mismatched now and I say, all right, well, there's 6 chlorines here. There's 3 chlorines here. So I'm going to multiply my compound that has chlorine in it by 2. So I can have 6 chlorines on both sides. And that multiplier of 2 is going to go out in front of my compound that contains chlorine. And that 2 is going to apply to my aluminum and it's going to apply to my chlorine. Okay. And then the last thing I'll have to do is come back over to my left side and say, all right, well, I have to make those aluminums the same now. So I'm going to have to multiply my aluminum by 2 as well. I'm going to put that 2 out in front of my aluminum. Okay. And at this point, I have a balanced equation. And I know this because my numbers all match up on both sides. Okay. And so the way that the answer choices here are written, they're just kind of listing them in order. So we'd have 2, and then we'd have 6, and then we'd have 2, and then we'd have 3. Okay, and if we look back at our answer choices, that's going to be choice C. All right. Let's also look at question number 3, which is another balancing question. Here they're giving us reactions that have polyatomic ions in them. Okay, so our first step again is going to be to make our table so that we can keep track of everything on the left and right side. Remember that when you have polyatomic ions that appear on both sides of your reaction unchanged, you can treat them as one unit as you balance. So I have got nitrate here and I've got nitrate here. I've got phosphate here and I've got phosphate here. That means I don't have to separate my polyatomic ion when I'm balancing my equation. Okay, so I'm going to keep track of my calcium, my nitrate, my potassium, and my phosphate. All right, and I'm going to do my count. So I've got 1 calcium, I've got 2 nitrates, so I can just write a 2 there and it's going to count for the whole nitrate. I've got 3 potassiums, and I've got 1 phosphate ion. And this is my phosphate ion. I only have 1 of them. Okay, I come over to my right side. I've got 1 potassium. I've got 1 nitrate. I've got 3 calciums. And I've got 2 phosphates. Okay, doesn't matter where you start here. Everything is part of a compound. And when you're looking at reactions where everything is part of a compound, it's not going to matter where you start in terms of your balancing. So I'm just going to start with calcium and move down. So I'm going to balance my calcium first. So I'm going to have to multiply my calcium compound by 3, which means I'm going to put a 3 out in front. Okay, and that 3 is going to apply to the calcium, but it's also going to apply to my nitrate ion. So I have to multiply my nitrate ion by 3 as well. So I'm going to have 6 nitrate ions on my left side. On my right side now, I've got 6 nitrates here. I've got 1 nitrate here. So I'm going to need to multiply my compound that has my nitrate in it by 6. So I have 6 of those as well. So I'm going to put a 6 out in front of my KNO3. And that 6 will apply to my potassium and my nitrate, which means I'm going to be multiplying my potassium by 6 as well. I can come back over here now and say, all right, well, my potassium, I've got 3 of them here. I've got 6 of them here. So I'm going to multiply my potassium compound by 2. So I can have 6 potassiums. So I'll put a 2 out in front of my potassium phosphate. And that 2 is going to apply to my potassium. And it's also going to apply to my phosphate ion. So I'm going to end up with 2 of those as well. And I see that all of my atoms on both sides of my equation match here. So that means my balancing is correct. And the combination of my coefficients here is going to be 3, 2, 6, and this is going to be a 1. When there's no number in front of your compound, you can assume that that coefficient is going to be a 1. Okay, so those are some examples of our balancing. All right. Let's look at the next set of questions. So here they're asking us which of the following reactions can be classified as decomposition. Remember that when we're looking at decomposition reactions, that means that we're looking for something to break apart into pieces as the reaction proceeds. So we should start with one thing and we should end on the product side with more than one thing. Okay. So as we go through these, we see that for choice A, we start with CuCO3. That's, one formula unit of this, one molecule, well, one formula unit. And it breaks up into two different substances. So we have one thing here that breaks up into two things. That's the definition of decomposition. Okay. Our second example, part B, we have two things that are smaller that combine together into one larger thing. That's going to be classified as a combination reaction. For choice C, we have magnesium by itself. We have silver nitrate that's part of a compound. And then on our product side, we have magnesium nitrate that's part of a compound, and we have silver by itself. So when we have one thing that takes the place of another thing in a reaction, that's going to be single replacement. Okay. And then here we have NaOH plus HCl gives us NaCl and H2O. This is a kind of convoluted double replacement reaction, but it's also a neutralization reaction. All right. But our Na and our hydrogen ion, these two things switch places. So we ended up with two H's and an oxygen and NaCl as our product. Okay. The next question, number 5, asks us the chemical reaction below is best classified as what type of reaction? And this is the exact reaction that we just looked at up here. So when we're looking based on our definitions of reactions, for something to be classified as a double replacement reaction, your cation in each of your starting compounds, it needs to switch place. It needs to switch spots with each other. Okay. And so your sodium should switch over to where the hydrogen was, and your hydrogen should switch over to where the sodium was for it to be a double replacement reaction. And we do see that that's what happens here. We end up with two new compounds, NaCl and H2O, and those are going to be formed from our cations switching spots. Okay, so that's going to be a double replacement. Let me just do little circles over here and over here visually so that you can see it in case. All right. Let's keep on scrolling. All right, we have some questions on redox now. It says in the following reaction, what is being oxidized and what is being reduced? So what we're going to do is we're going to write down this reaction and we're going to try to track where the electrons are going. Okay, like we talked about in class, based on the oxidation numbers, which behave a lot like charges. Okay, so remember that part. They behave a lot like charges. So we have Cl2, 2NABr, two NaCl, and Br2. Should make that aqueous as well. Okay. So when we're looking at each of these, think about logically what the charges in each of these substances are going to be. When you have atoms, when you have elements by themselves, whether they're monoatomic elements or they're diatomic elements like we have here, when you have elements, they're always going to have an oxidation number of 0. Okay. So our Cl2 and our Br2 are both going to have oxidation numbers or oxidation states of 0. Okay. when they join a compound or when they're forming compounds, the elements that are part of those compounds are going to have oxidation numbers that are different than 0. So when the elements are by themselves, they're 0. When they're part of compounds, they're going to change from 0. And you can look at the likely charges of the elements that make up your compound to help you figure out what the oxidation number of your elements that are part of your compounds are going to be. Okay. We talked about the list of rules. So if you still have your list of oxidation rules, you can use those as a reference too. We know that sodium is a group 1 metal, so it's going to have an oxidation of +1 like all other group 1 metals. And our bromine has to have a -1 to balance out sodium's +1. Okay, so each individual element is going to have its own oxidation number, which again, it looks a lot like a charge. So you could think about them like that if it's helpful. Over here with our NaCl, you see that our sodium has a +1 again. And this time it's going to be our chlorine that has a -1. All right. When you're deciding what's being oxidized and what's being reduced, you're going to be looking for the changes in the numbers. Okay. So we see that chlorine's number changes from 0 to -1. We see that bromine's number changes from -1 to 0. And we see that sodium's number does not change. Okay. So for our sodium, it's not being oxidized or reduced. Nothing is happening with the sodium. But for our chlorine goes from, we could just say our chlorine in general goes from 0 to -1, right? So it's getting more negative. If something's getting more negative, that means it's gaining electrons. So that means that our chlorine is reduced. Okay. The chlorine that's part of our Cl2 is going to be reduced. If we track our other change, that's from our bromine with its -1 charge to its bromine that's neutral, right? It goes from -1 up to 0. So our bromine that's in the Br-1 state, right? It's a part of your NABR. It's going to go from a -1 to a 0. So it's going to be getting more positive. If it's getting more positive, that means it's going to be losing electrons. And remember what we said about like remembering oxidation and reduction. When it's losing electrons, it's oxidation. When it's gaining electrons, it's reduction. So our Br minus in the NABR is oxidized. Okay. So we have, yes, that looks like it's choice B on our answer key. Yeah. Just trying to make sure I didn't switch the numbers. Nope, I definitely did. I just read that opposite. Our Br minus in NABR is oxidized. That's choice D. And our Cl2 is reduced. Sorry about that. Yeah, that matches up with choice D in our answer key. All right. So again, tracking the charge changes is going to be the easiest way to tell what's being oxidized and what's reduced, especially if you're looking at a reaction where you don't have actual charges written into the reaction itself. Question number 7 gives us another reaction to look at and asks us which element is undergoing reduction. Okay, and it gives us this reaction. Okay, and we're going to kind of treat this the same way as we were going through our other question. We look at the reaction and we look for things. First of all, I look at my elemental oxygen here, and I know that it's going to have an oxidation of 0. I'm going to remember from my list of oxidation rules that hydrogen is going to have a +1 oxidation number, and there are 4 of them, which is going to give me a total of +4. That means that my carbon has to be a -4 so that these cancel each other out. Over on my product side, I'm going to have 2 oxygens. Each oxygen will be a -2 for a total of -4, which means my carbon is going to be a +4. Okay, to again cancel the charges out. And then for my H2O, I'm going to have 2 hydrogens and 1 oxygen. Okay, and now I'm going to look at the difference, the change in any numbers that happen. I see right away that I have no change in the numbers for my hydrogen. They're +1 on both sides. That's fine. That just means there no oxidation or no reduction is happening with hydrogen. For my carbon, I'm going from a -4 to a +4. So my carbon gets more positive, which means it's oxidized. Okay. I'm looking for the thing that's being reduced. So I need something to be getting more negative. I have my oxygen, it's going from a 0. It's not being reduced when it goes into the carbon dioxide, but, oh no, it is. It's for both of them. It's going from a 0 to a -2. So in both cases here, my oxygen for my O2, it's getting more negative as I go to my product side. So when my oxygen gets more negative, that means that it's undergoing reduction. Because if it's getting more negative, then it's gaining electrons. Okay. So here I was losing electrons. Here I was getting more negative. So I gained electrons. All right. Let's look at our next question. All right, so in question number 8, it's asking which statement is a true statement. So there's 5 statements here. If it's asking us for the true statement, that means that 4 things should be wrong and only 1 statement should be right. Okay. So we should be trying to pick out the 4 incorrect statements. So first statement, in a reaction, oxidation can occur independently of reduction. That's not true. That's never going to be true. these things always have to happen together. You can never have oxidation happen without reduction. You can never have reduction happen without oxidation. Okay. Second statement. A redox reaction involves either the transfer of an electron or a change in the oxidation state of an element. It's both of those things that are always true. This or, that makes the statement false, because both of those things are going to happen in any oxidation reduction reaction. So that one's no good either. If any of the reactants or products in a reaction contain oxygen, the reaction is a redox reaction. That's not true. There are plenty of redox reactions that are that can happen that contain oxygen, and the oxygen is not being oxidized or reduced as a part of that reaction. Choice D, oxidation and reduction must always occur together. That right there is our true statement. Choice E, oxidation reduction reactions must contain hydrogen and oxygen. That's not true. Many of them do, but they do not have to contain hydrogen and oxygen. Okay. All right. Let's look at our next question. We have 2 math questions coming up next. So question 9 is asking us for the number of carbon atoms in 0.5 moles of carbon. Okay, so we'll start here. Remember that when we're talking about elements, we can use Avogadro's number to go between moles of an element and atoms of an element. Okay, use Avogadro's number for this. For elements, Avogadro's number can be written as 1 mole of that element equals 6.02 times 10 to the 23 atoms of that element. All right. So here, they're telling me I have 0.5 moles of carbon. So if I have 0.5 moles of carbon, then when I set up my conversion factor, I'm going to base it on this equality. My 1 mole part of it is going to go on the bottom so that it cancels out with my mole unit that was up here that I was given originally. And my 6.02 times 10 to the 23 carbon atoms goes up top. Okay. And we're going to end up with 3.01 times 10 to the 23 carbon atoms as our final answer there. All right. In question number 10, we're going to be incorporating a compound into our calculation here. They're asking us how many moles are there in 120 grams of glucose. Okay, so our relationships for compounds are, I would say that for every question that you are working out mathematically, make yourself a roadmap for that question. Okay, so here they want us to connect grams to moles. The only way that you can make this connection is going to be to use the molar mass. Whether you have an element or a compound, using the molar mass is how you're going to be able to convert back and forth between grams of that substance and moles of that substance. So to find the molar mass, we have to look at our chemical formula. We have 6 carbon atoms, 12 hydrogen atoms, 6 oxygen atoms, right? And so we're going to make a little, like we're going to keep count of what we have here. 6 carbon, 12 hydrogen, 6 oxygen. We're going to look on our periodic table for the molar masses. And then we're going to, we'll do it out dramatically one time. Okay, and then we'll add all those together. And we're going to cut it off. We're going to round it to 2 decimal places. So 180.16. And when we're looking at molar masses, remember that we can always write out that molar mass as an equality. So when we get this 180.16, what that means for us is that there's going to be 180.16 grams in every 1 mole of our glucose. Okay. That's important for us because we're trying to connect grams of glucose and moles of glucose. They've given us a value in terms of grams of glucose. And so when I set up my conversion factor, I'm going to want my grams of glucose on the bottom. So I'm going to put my 180.16 grams down there. And I'm going to put my 1 mole of glucose up top. Okay. And when I do my division, I'll round it to 2 significant figures here. And I'm going to get 0.67 moles of glucose. Okay. All right, let's look at our next questions. All right. So question number 11 says, how much does Avogadro's number of sulfur atoms weigh? All right. So to answer a question like this, we have to know a little bit about the definition of molar mass. Okay. Remember that we can look at the periodic table. We can look at those numbers that are listed beneath our elements on the periodic table, and we can and we have used the unit AMU to represent that number before. Okay, remember AMU means atomic mass unit. But when we're talking about masses, when we're talking about how much things weigh, mass units are units of grams, milligrams, pounds, our actual mass measurement value. Okay. So right away, when you look at a question like this one, the first thing that they're trying to really see if you understand is by them asking how much this weighs, do you understand that we are not going to be including the answer choices that have AMU as their unit? We're going to focus in on the answer choices that have grams as their unit. All right. The second part of this question is knowing what the definition of Avogadro's number is. Okay. I'm going to write in my very chaotic mouse handwriting, but Avogadro's number is equal to 1 mole. Okay. And our molar mass units are listed in grams per 1 mole. So if I'm looking for Avogadro's number of sulfur atoms, that means I'm looking for 1 mole of sulfur atoms. And I can use the number on my periodic table to tell me how much 1 mole of sulfur atoms weighs. The number on the periodic table for sulfur is 32.07. So out of these two answer choices, I would pick choice D to represent the grams that would be present in 1 mole of sulfur atoms. Okay. Moving on to question number 12, they're asking us here to calculate the molar mass of pentanol. So we are going to write out the formula that they give us, and then we're going to do a calculation. The way they've written out this formula is going to be a good reminder to us about how to use parentheses when they're given to us in the chemical formulas. Okay, and we're going to calculate the molar mass. Okay, so the first thing we want to do is we want to count up the number of atoms of each element that we have. So we have carbons in this compound, we have hydrogens in this compound, and we have oxygens. Well, we have 1 oxygen. Okay, so for our carbons, we'll start there. We've got a carbon here, we've got a carbon here, and we've got, remember, the subscript that's outside of the parentheses, it applies to everything inside of those parentheses. So that's telling me that within the parentheses, I've got 3 carbons, and within the parentheses, I have 3 times 2 or 6 hydrogens. Okay. So I've got 3 carbons, 4 carbons, 5 carbons total. For my hydrogens, I can start within the parentheses just to make it a little bit easier. 3 times 2, I've got 6 hydrogens in my parentheses, plus 3 more here. So 7, 8, 9, plus 2 more here. It's 11, plus 1 more here, 12. And I've got 1 oxygen. And from here, I am going to use the molar mass from the periodic table for each of these elements. And then I'm going to add those together. And I'm going to get 88.146 grams per mole, which is my unit for molar mass. And that is going to match choice C on my my answer choices. Okay. Right, let's take a look at question number 13. It's asking us to calculate the mass in grams of 2.40 moles of aluminum oxide. So before we can start on this question, we're going to have to calculate the molar mass of our aluminum oxide. So put our molar mass calculation here. We've got 2 aluminums. We've got 3 oxygens. Okay, I'm going to add those together. Okay, and remember that when you have a molar mass, you can rewrite it as an equality. Which might help you when you're setting up your conversion factors. Okay, so now we set this up. And we have, the question is how many grams are going to be in 2.40 moles of Al2O3. And we know from our conversion factor that every 1 mole of Al2O3 is going to be 101.96 grams. So our moles of Al2O3 can cancel out. And we're going to end up with 245 grams of the aluminum oxide. That would be choice D on your multiple choice. All right. The next questions, they don't really go together, but they go together in that they both share the same reaction that we'll need to balance before we can answer the questions. Okay, so the first off, 14 and 15, they give us the reaction. Okay, and the first thing that we're going to have to do is balance this reaction. Okay, we can't answer any of the questions that they're asking us until we balance this reaction. So we're going to start out following our balancing technique. All right. Right now, the only thing that's not balanced is our oxygens. And so we are going to balance those first. So we'll multiply our oxygen compound by 2 to give us 6 oxygens. We can multiply our oxygen on the right side by 3 to give us 6 oxygens. And we're going to multiply everything else in the compound by 2 as well on our reactant side. So we're going to have 2 potassiums, we're going to have 2 chlorines. That means that on our product side, we'll have to multiply our potassium and our chlorine by 2 as well. So we'll put a 2 in front of our KCl as well. And that's going to be our balanced equation. Now that we have a balanced equation, we can answer the questions that we were asked. Number 14 asked, how many moles of oxygen can be produced from 1 mole of KClO3? So how many moles of oxygen are going to be in 1 mole of KClO3? And so what we're going to do is we're going to set up an equality that we can use in our conversion factor. And it's going to be the equality between oxygen and KClO3 from our reaction here. And from that reaction, what we can see is that every 2 moles of KClO3 are going to produce 3 moles of oxygen. Okay. With that equality, we can answer this question now, because if we have 1 mole of KClO3, we know that every 2 moles of KClO3, we put the KClO3 in the bottom because we want matching units on opposite sides of the fraction bar so that they cancel out. So every 2 moles of KClO3 produces 3 moles of oxygen. Okay, 3 divided by 2, 1.5 moles of O2 are produced. Okay, and that's going to be choice B. For question number 15, they make it a little more complicated for us because they ask us how many grams of oxygen can be produced from 100 grams of KClO3. All right, so we can't jump right into our mole to mole conversion. If we're given a number, or if we're given a mass value to start with, our first step is going to always be to take that mass value and turn it into moles of that same substance. Okay, using our molar mass. So we're going to take our grams of KClO3 and we're going to turn it into moles of KClO3. And we're going to do that using our molar mass value. Once we have moles of KClO3, then we can switch it to moles of oxygen using our balanced equation, using our coefficients, our equality that we pulled out for the last example. And once we have our number converted into moles of oxygen, then we can convert that back into grams of oxygen by using the molar mass of oxygen, of O2. Okay, so this step is going to be molar mass. This step is going to be our balanced equation. And then this step is going to be the molar mass of oxygen. All right. We can calculate the molar mass of KClO3 real quick on the left side, and we'll calculate the molar mass of O2 on the right side. So for our KClO3, we're going to have 1 potassium, 1 chlorine, and we're going to have 3 oxygens. Okay, and we'll put a little plus sign there so we know we're adding them all together. And for our O2, it's going to be 2 times 16. All right. Okay, so if we have 100 grams of KClO3, our first step is going to be to turn it into moles using our molar mass. So we're going to put our 122.5 grams on the bottom so that our gram numbers cancel out. And our 1 mole of KClO3 up top. And then in our next step, we're going to use our relationship between moles of KClO3 and moles of oxygen. Right? So we're going to put our moles of KClO3 on the bottom so that these can cancel out. and we'll put our 3 moles of oxygen up top. Okay. And then in our last step, we're going to go from moles of oxygen to grams of oxygen. For every 1 mole of O2, we're going to have 32.00 grams. And we end up with 39 grams of O2, which is also choice B. Okay. All right. Next question. We're going to be looking at a limiting reactant and a theoretical yield. All right, so let's write down the reaction first. The question tells us determine the limiting reactant and the grams of product obtained if 25 grams of each reactant is initially present. With questions like these, I know you've seen this in some of the other videos that I've made. I like to write down, once I have my balanced equation written out, I like to write down my mass amounts or whatever information I'm given about each reactant or each product. I like to write it down underneath within the balanced reaction that I'm looking at to like keep track of it. So they're telling us here we have 25 grams of each of these starting things, and they're asking us to find the limiting reactant. And they're asking us to find the grams of product obtained, which is the same thing as the theoretical yield. Okay. So in order to do both of these things, whenever you have a problem where there is a limiting reactant, and you'll know that it's a problem that has a limiting reactant when you're given 2 quantities of reactants, right? Because if you have 2 quantity values for your reactants, that means that you have to determine which of those reactants, which amount is going to run out first. And whichever one runs out first, that's going to be our limiting reactant. Okay. So if you have a reaction with 2 reactants, then your first step in any question like this is to do 2 calculations, each calculation telling you how much product your reactants can produce. So we're going to do a calculation for the silver. So for our silver, we have 25 grams of silver. We're going to go from grams of silver into moles of silver. And then we're going to go from moles of silver into moles of AgCl. And then we can do our comparison at that point. Okay, and we can find the gram value after we figure out the limiting reactant. So my first step when I go from grams of silver to moles of silver, this first step has to be done using the molar mass. Anytime you go between grams and moles, that's a molar mass value that you're going to need. The molar mass for silver is 107.87. And you can do this in like a two-step process if it makes it easier for you to understand too. Like we can do this first step and we can just look at the moles of the silver. And then in our second step, we can convert our moles of silver into moles of AgCl. And for this step, we look at our balanced equation. We have 2 moles of silver for every 2 moles of AgCl. Okay. Now we're going to do the same exact sequence of steps, but we're going to do those for the chlorine instead. Okay. So for our Cl2, I also have 25 grams. But for my Cl2, my molar mass value is going to be the molar mass for chlorine times 2, right? Because the formula is Cl2. So I'm going to have 70.90 grams of Cl2 for every 1 mole of Cl2. And then I'm going to look at my balanced equation, and I'm going to see that every 1 mole of Cl2 makes 2 moles of AgCl. Okay. Those are the 2 values for AgCl that I'm going to get from these calculations. When you're looking at the numbers and you're starting to compare the product values that you have, that larger value that you've calculated, I strongly recommend that you just put an X through it because you are not going to need that number. And it's better if you physically mark for yourself that you do not need that number so you don't accidentally use it for something else. Okay. What we have with the information that we've collected so far, what we know that this value here, this is our theoretical yield in moles. Our final answer needs to be in grams, but we can get that very easily now that we have this number. And we also know that the reactant that formed our theoretical yield, which is silver, this is our limiting reactant. Okay. So our limiting reactant is going to be Ag. So we can already cross out choices C and D because we know that those are not going to be correct. And now we can take this value our theoretical yield that's in moles. And we're going to let's do a molar mass calculation for our AgCl real quick. Okay, so we have 0.2318 moles of AgCl. And we know from our molar mass that every 1 mole of AgCl is going to be 143.32 grams. So I'm going to end up with 33 grams of AgCl at the end of my reaction when I run out of silver. Okay. So my limiting reactant is silver, and I'm going to have 33 grams of my AgCl. That is going to be choice A out of my multiple choice options. Okay. Now we'll look at question number 17. Question number 17 asks about the percent yield. What is the percent yield if 100 grams of C3H8 combusts to produce 200 grams of CO2? Okay, and they give us our reaction. So we have C3H8 plus 5O2 produces 3CO2 plus 4H2O. Okay. And the information that they've given us here, they've told us that we're starting with 100 grams of our C3H8, our propane, and we're going to be able to produce 200 grams of CO2. Okay. This information here, when it tells us that we're able to produce 200 grams of CO2, they're telling us how much CO2 that we are able to collect, that we're able to make at the end of the reaction. The product value that they're providing us in the information that we're given, this is going to be our actual yield. Our actual yield is going to be the product information specifically the amount of product that we have. That's provided to us in the question. And it's going to represent the amount of product we actually ended up with. Okay. Our percent yields is going to be our actual yield, which they'll have to give us, divided by our theoretical yield, which we will have to calculate, times 100. So this value here, we calculate this from the reactant value given to us. Sometimes more than one value. Okay. So they're telling us that we collected 200 grams. We're going to use this information to see how many grams of CO2 we should have been able to make. Okay. So let's do some molar mass calculations before we start. We're going to need a molar mass for our propane. C3H8. And we'll need the molar mass for CO2. Sorry, that should say 12 a little more clearly. Okay, so those are the molar masses that we're going to need for these calculations. So we're going to take our grams of C3H8. We're going to convert it into moles of C3H8. Then we're going to use our balanced equation to convert it into moles of CO2 and then into grams of CO2. And this value here, this is going to be how we calculate our theoretical yield. Okay, so we've got 100 grams of C3H8. We said there's 44.09 grams in 1 mole. Step 2, we're going to go from moles of C3H8 to moles of CO2. We see from our balanced equation, there's no number in front of the propane, so we'll just imagine a number 1 there. It's an implied 1. So every 1 mole of C3H8 is going to produce 3 moles of CO2. And then we're going to go from moles of CO2 to grams of CO2. So we'll have 1 mole of CO2 on the bottom, 44.01 grams of CO2 up top. Okay, so we should have been able to make 299 grams of CO2. But we only made 200 grams of CO2. So now to calculate our percent yield, we're going to take our 200 grams, which is going to represent our actual value, divided by our 299 grams, which is how much we should have been able to make, our theoretical value, times 100. And we're going to get a percent yield of around 67%, which would be answer choice C. All right. Let's look at the next couple questions, get those up. All right, our first question here, number 18, says the enthalpy of solution, which is another way of saying the delta H value for the reaction. So the enthalpy of the solution for ammonium nitrate is 25.7 kilojoules per mole. And it wants to know whether that makes the reaction endothermic or exothermic. The sign of our enthalpy of solution or heat of reaction, enthalpy of reaction, there's a few ways to say this that all kind of mean the same thing. But when that value is a positive value, that means that your reaction is going to be absorbing heat. Heat's going to be entering your reaction. And your reaction is going to be endothermic. Okay, so a positive delta H, endothermic reaction. If this number was negative, you'd have an exothermic reaction. Okay. All right, let's look at question number 19 next. How many kilojoules are released when 100 grams of NO reacts? So here they give us our balanced reaction. They tell us that our delta H value is negative 114 kilojoules. So with this information, we know that the reaction is going to be exothermic. And we know that we can represent heat as a product. So if we were going to add it into our reaction, we would put it on our product side. We would say that 114 kilojoules of heat is going to be released or produced as a product, and it's going to leave into the surroundings. Now it's helpful to write your reaction out like this, two of those, 4, 5, 6. Sorry, I'm just looking at the reaction as it was written there. I think that they meant to not have the 2 there. Yeah, okay. Yeah, there shouldn't have been a 2 there. Just that looks like it was a typo. Yeah, because now we have 2 nitrogens and 4 oxygens. Oh no, we don't. Now we have, yeah, 2, we have 4 of those. Okay, cool. When you have the balanced equation written out like this, you can make equalities between not only your reactants and products, but also the heat value that was either absorbed or released. This question asks how many kilojoules of heat are released when 100 grams of NO reacts. So it's asking us to find the kilojoule value that goes along with the 100 grams of NO. The equality that we can make between those two things is that coefficient in front of our NO value. Every 2 moles of our NO gas is going to produce 114 kilojoules of heat. So we can use that equality and we could say, all right, well, I'm going to start with my grams of NO and I'm going to use my molar mass to turn it into moles of NO. And once I have my number in moles of NO, I'm going to use my equality that I've got from my balanced equation to turn it into kilojoules of heat. Okay. We can break these types of problems down into steps as well. You don't always have to do them in that one single solution line. Step 1 here, when we do our first conversion, we're going to use the molar mass of NO for this. So we need the molar mass of NO for that. So nitrogen is going to be 14.01. Oxygen, 16. Okay, so 30.01 grams per mole for that. So if I'm starting out with 100 grams of the nitrogen monoxide gas, in my conversion factor, I'm going to put my grams value on the bottom so that it cancels out. And my mole value up top. Okay. In step 2, I'm going to use my balanced equation to go from moles of NO to kilojoules of heat. So I've got 3.33 moles of NO. And I know that every 2 moles of NO are going to release 114 kilojoules. And I'm going to end up with 190 kilojoules of heat are released, which can also be represented with a negative sign. That negative sign is going to kind of be representing the fact that our reaction is going to be losing that heat amount. Okay, so this for us is going to be answer choice C. This was question 19. Okay, we have some more limiting reactant questions coming up, it looks like. All right, so I'm just going to write out the reaction first. And I would recommend, again, writing the values from the question underneath the components of your balanced reaction where you find them. So my 20 grams of AgNO3, I'm just going to write it down here. And my 15 grams of CaCl2, I'm going to write it over here. That way, it should be really clear to you when it is a limiting reactant question, even if they don't use the word limiting reactant, because you're going to have 2 mass amounts for your products, or for your reactants rather. And if you have 2 reactant masses, then your question is always a limiting reactant question. So this question says, in the following reaction, how many grams of AgCl will precipitate when 20 grams of AgNO3 reacts with 15 grams of CaCl2? So these 2 things are going to react together. They're going to form AgCl. And we need to know how much AgCl is formed when our limiting reactant runs out. Okay, we don't know which one is limiting yet, so we have to do the calculation for both of them. So for our AgNO3, we're going to start with our 20 grams. And then this first calculation, we're going to use our molar mass for AgNO3. Let's write down some molar mass values over here. So our AgNO3 is going to be 107.87 plus 14.01 plus 3 times 16. Okay, we need a molar mass for CaCl2. So that's going to be 40.08 plus 2 times 35.45. And we're going to need a mass for AgCl, which I know we calculated before, but I don't remember it. 107.87 plus 35.45. Okay, so those are our molar mass values. So we can use those as we need them. So we'll take our 20 grams of AgNO3. There's 169.88 grams of AgNO3 in every 1 mole. Okay, and then we are going to look at our mole ratio. There's 2 moles of AgNO3 in every 2 moles of AgCl. Okay, so that's how much AgCl we can form if we use up all of our silver nitrate. Now we're going to do the same thing for the calcium chloride. Here we've got 15 grams. There's 110.98 grams in every 1 mole. Forgot to cross out my units there. And there's 1 mole of calcium chloride for every 2 moles of silver chloride that form. Okay, we got those 2 values. Again, because this is a limiting reaction type of question, 100% right away, the bigger number, cross that out so you don't accidentally use it. You're going to focus in on this value here. Your 0.1177, the number here is represented in moles. All of those answer choices are in grams. So we're going to take this value and we're going to convert it from moles of AgCl into grams of AgCl using our molar mass for AgCl that we've already calculated. So every 1 mole It's going to be 143.32 grams. Which means that 16.9 grams of AgCl will form. Okay, which was choice A. All right, and question number 21. It's another limiting reactant type question, but they're asking us to pick out the true statement from the list of statements that they give us. Okay, so we're going to have to kind of calculate the limiting reactant and the theoretical yield for us to figure out, like which thing is going to be the true thing. The first choice they give us in this question, they say that the equation is not balanced. That's our first statement that we have to check to see if it's true or false. This is the reaction that they give us. So the reaction is balanced, so it's not going to be that statement. So we're going to be starting with 8 grams of H2 and 9 grams of O2. We should be able to figure out the limiting reactant from both of those values. Okay. We'll start out with H2. So we have 8 grams of H2. Our first step is going to be to convert our grams of H2 into moles of H2 using our molar mass value for H2. And then we're going to use our balanced equation to relate our moles of H2 to our moles of H2O. Okay, now we have to do the same thing for the oxygen. We have 9 grams of oxygen. We know it's O2, so there's going to be 32 grams of O2 for every 1 mole of O2. And from our balanced equation, we know that every 1 mole of O2 is going to give us 2 moles of H2O. Okay. So we can compare these two numbers right away. We know that that's no good. This is going to be our theoretical yields in moles, which means that oxygen is going to be our limiting reactant. So right away, we know that choice C is going to be the correct choice, but we can also disprove choices D and E if we want to. 0.5625 moles of H2O is the mole value of water that will be produced. So choice D is incorrect. And then if we want to take the molar mass of H2O and use it to figure out how many grams of water we actually end up with. It should be like 10 grams of water. So these two values here represent our theoretical yield values for the water. So choice D is wrong and choice E is wrong. Choice C is the right answer. O2 is the limiting reactant. All right. Let's share the next two questions. So we have a percent yield question, and we have another limiting reactant slash theoretical yield question that we're going to look at here. All right, so let's start with our percent yield question. We'll write down the reaction because that's always a place you always want to start with writing out the reaction and then kind of keeping track of the information that they're giving you. Okay, so they're telling us 22.4 grams of the KO2 react with an excess of water. So they're telling us the KO2 is going to be our limiting reactant because our water is going to be present in an excess amount. We're going to have plenty of water. And it's going to produce 13.9 grams of KOH. Again, when they give us a reactant amount and they give us a product amount, this product amount that they give us, this represents our actual yield. Okay. And we have to use our reactant amount and we have to find the theoretical yield. Okay. We have to find the theoretical yield so that we can calculate the percent yield. So to find our theoretical yield, we're going to take our 22.4 grams of KO2 and we're going to turn it into moles of KO2 first using our molar mass. Then we're going to convert our moles of KO2 into moles of KOH using our balanced equation coefficients. And then we're going to convert our moles of KO2, KOH rather, into grams of KOH using our molar mass. Okay. So this first step, we're going to do the molar mass of KO2. Second step, our equation coefficients. Third step, molar mass of KOH. And once we have this value, this is going to be our theoretical yield value. And then once we have our theoretical yield, we can calculate our actual yield value. Yeah, so 22.4 grams, we're going to use this to find the theoretical yield. So we're going to start out, we'll need to know our molar masses for KO2 and KOH. So KO2 is going to be 39.1 plus 2 times 16. So it's going to be 71.1 grams per mole. And our molar mass for our KOH. Okay. So we're going to need those two values when we're calculating this. So step one, we'll do our grams to moles. So we have our 22.4 grams of KO2. We know that there are 71.10 grams of KO2 in every 1 mole of KO2. Okay. Step 2, we're going to take our moles of KO2 and we're going to convert it into moles of KOH. So from our balanced equation, every 4 moles of KO2 is going to produce 4 moles of KOH, which means that we'll also have 0.315 moles of KOH. Step 3, we're going to take our moles of KOH and we're going to turn it into grams of KOH using the molar mass of KOH. Every 1 mole of KOH is going to be 56.11 grams. Okay, so this value right here, this is our theoretical yield. Okay, now that we have the theoretical yield, now we can calculate our percent yield. So our percent yield is going to be our 13.9 grams, which is our actual yield, divided by our 17.7 grams, which is our theoretical, times 100. And we get a percent yield of 78.5%. Which was answer choice A. Okay. The next question, number 23, asked us to determine the limiting reactant and calculate the number of grams of P2O5 that can be formed. Okay, and they're giving us 115 grams of phosphorus reacting with 215 grams of oxygen. Okay. So first things first. We'll start out with our phosphorus. Grams of phosphorus to moles of phosphorus using our molar mass to moles of P2O5 using our balanced equation. Okay. So we have 115 grams of phosphorus. We're going to look at the molar mass of phosphorus. It's 30.97 grams in 1 mole. Okay. Next step, we're going to go from moles of phosphorus to moles of P2O5. 4 moles of phosphorus for every 2 moles of PTO5. Notice that if moles of phosphorus is what we start with, then moles of phosphorus is what goes on the bottom of the fraction when we make up our conversion factor so that it can cancel out. Okay. Now we can pause here a second because we can do our comparisons with our P2O5 in terms of moles, and we can focus on the oxygen. We'll do the same set of steps for the oxygen, but I'm going to combine this so we have one continuous solution, right? Because we want to get used to seeing these not broken up, all right? Just because it's more common to see your dimensional analysis, your conversion factors laid out one after the other. So if we start out with 215 grams of oxygen, our first step is going to be to take our molar mass of oxygen and find moles of O2. Our next step is going to be to use our coefficients in our balanced equation to show us that every 5 moles of O2, we're going to make 2 moles of P2O5. Okay, so right here with these two numbers, we can cross out the bigger one, and we know right away that oxygen is not our limiting reactant. Okay, so our limiting reactant is definitely our 115 grams of phosphorus. Now we have to figure out how much phosphorus in grams is formed. We already know how much phosphorus in moles is formed, or sorry, how much P2O5 in moles has been formed. But we're going to take this mole value and we're going to figure out the mass of P2O5 that was formed by using the molar mass. So the molar mass for our P2O5 is going to be 2 times 30.97. That's our mass for our phosphorus, plus 5 times 16, which is the mass for our oxygens. Okay, so this is how many moles of P2O5 that we formed or that we should be able to form. And we know that every 1 mole has a mass of 141.94 grams. And so we should be able to make 264 grams of P2O5 from our 115 grams of phosphorus. So that's going to be answer choice B. All right. Let's take a look at the next questions up here. Okay, so we'll look at questions 24 and 25 next. 24 is asking us to find the mass of the CO2 that's produced from the decomposition of 25.5 grams of NaHCO3. So we'll be relating these two things. And question 25 is asking us what mass of AgCl will precipitate when 10 grams of silver nitrate is added to an aqueous solution of NaCl. So we're going to have 10 grams of silver nitrate, and we want to see how much silver chloride is going to form from that. Okay. They're telling us we've got 25.5 grams of this. I would say that for this problem, because we know that we're going to be looking for mass values, that it would be a good idea to, again, get those molar masses calculated earlier rather than later so that we have them. So let's just find the molar mass values over here. All right, all of that is the molar mass for our sodium hydrogen carbonate. And then for our CO2, we got 12.01 plus 2 times 16. Okay. And that's our setup. We have 25.5 grams of this. We want to know how many grams of this are going to form. Okay. So step one, we're going to take our 25, well, we can map out the steps. We're going to go from grams of NaHCO3, convert that into moles of NaHCO3. Then we're going to use our equation here, even an equation like this one, where all of the coefficients are 1. It's a good idea not to skip this step when we're going from moles of NaHCO3 to moles of CO2, because most of the time, with the exception maybe of these next two questions we're doing, most of the time the coefficients are going to impact your final answer. So you don't want to get used to skipping this particular step. You'll end up with the wrong answer when you're done. So grams of NaHCO3 to moles of NaHCO3, moles of NaHCO3 to moles of CO2, moles of CO2 to grams of CO2. Okay, that's our setup steps. So we have 25.5 grams. We see from our molar mass that there's 84.01 grams in 1 mole of our sodium hydrogen carbonate. We see from our balanced equation that for every 1 mole of the sodium hydrogen carbonate, there's 1 mole of CO2. And we see from the molar mass of CO2 that every 1 mole of CO2 is going to be 44.01 grams of CO2. Okay, which is going to be choice C. Now let's look at question number 25. It's going to be real similar in terms of the steps that we want to do. Our reaction that they give us is NaCl plus AgNO3 produces AgCl plus NaNO3. Okay. Like as was mentioned in the question, this is another example of a decomposition reaction. This is an example of a double replacement reaction. So again, it's really good to recognize those when you see them. We're going to be starting off with 10 grams of AgNO3, and we're going to be figuring out how many grams of AgCl are going to form. So let's write down the molar masses for these two things because we're going to need them. So for our AgNO3, it's going to be 107.87. Let me actually write down the plus 14.01 plus 3 times 16. And then for AgCl, okay, so these will be our 2 molar mass values that we'll need for this question. The format's going to look awful similar to what we did up here because we're going to take our grams of AgNO3. We're going to turn it into moles of AgNO3 using our molar mass. We're going to convert it into moles of AgCl using our balanced equation. And then grams of AgCl using our other molar mass. Okay. So 10 grams of AgNO3 to start with. Okay, that's step 1. Now I'm going to go from moles of AgNO3 to moles of AgCl using our coefficients in our equation. Everything's 1 in this equation, so 1-to-1 ratios, nice and easy. Okay, and then our last step, we're going to use our other molar mass. Every 1 mole of AgCl is 143.32 grams. Okay, and we end up with 8.44 grams of AgCl, which is going to be answer choice B. Next questions. Question number 26. All right, we've at least got some more interesting coefficients in these next couple questions. So we're going to be going from grams of NO2, figuring out grams of oxygen in question number 26. And we're going to be going from grams of potassium into grams of hydrogen for question 27. Right. So in both of these examples, those coefficients are going to make a huge difference in our final results. Okay, so they're telling us that we are going to produce 75 grams of NO2, and they want us to figure out how many grams of oxygen we're going to need for that. Okay, so these are the two things that we're going to be connecting. For our molar masses, NO2 is going to be 2 oxygens plus, let me get that down there a little bit, 2 oxygens plus 1 nitrogen. So it's going to be 46.01 grams per mole. And our molar mass for O2 is going to be 32 grams per mole. All right, so we start out with our, in this case, we're going to be going from grams to NO2, grams of NO2 into moles of NO2. From moles of NO2 to moles of O2. And then from moles of O2 into grams of O2. All right. So I've got 75 grams of NO2. Then my first step is going to use the molar mass, which says I have 46.01 grams of NO2 in every 1 mole of NO2. My second step, I'm going to be relating moles of NO2 to moles of O2. So this is where I use my coefficients. There's 4 moles of NO2 that are produced for every 7 moles of O2 that are reacted. We can watch our units cancel out as we go. Our final step, every 1 mole of O2 is going to be 32 grams. Okay, and we're going to end up with 91.3 grams of O2. That's how much O2 we're going to need to form our 75 grams of NO2. And that's going to be choice E. All right, let's question number 27, different reaction. Same set of steps. They're all real. Everything's linked once it starts making sense. Okay, here they say what mass of H2 is produced when 15 grams of potassium reacts with water. So in this case, we're going to be going from grams of potassium into moles of potassium into moles of our hydrogen, our H2, and then into grams of our hydrogen. our molar masses that we're going to need for this part. The molar mass for potassium is 39.10 grams per mole. The molar mass for H2 is going to be 2.016 grams per mole. Just switch out markers. That one's getting tired. All right, so we start out with our 15 grams of potassium. "39 grams of potassium and 1 mole of potassium." And then we look at our balanced equation. There's 2 moles of potassium for every 1 mole of H2. And every 1 mole of H2 is going to have 2.016 grams. Okay, and we end up with 0.387 grams of H2 that are going to form. That's answer choice A. All right. Our next 2 questions are balancing questions. So I'm going to share the screen again, just to take a look before we start balancing. All right. So for our first one, they're asking us specifically what the missing equation in front of the carbon dioxide is. So this is going to be the one that we're going to focus on when we're balancing these. I mean, you have to balance the whole equation in order to figure out this coefficient, which makes questions that are set up this way a little more difficult because you do have to balance the entire thing. You can't just test out all the coefficients that are provided and see which one makes sense. Okay. So we want to have a good process for balancing that we can use in a situation like this, where we're not given those sets of coefficients to use. All right. So the first thing we're going to do, just like before, we're going to split our reaction up into 2 halves, and we're going to keep track of our elements on each side. And I would recommend on your product side for this one, because we have oxygen that's present in carbon dioxide and in H2O, I'd recommend making like a little branch here and keeping the 2 oxygens from the CO2 and the 1 oxygen from H2O separate from each other, just so that you can keep track of them individually and then add them together. So like we have 2 for the CO2, we have 1 for the H2O, and we have 3 altogether. Okay. We have 1 carbon and we have 2 hydrogens. Okay, so the first thing that we can do is balance the carbons and the hydrogens out. We know we'll have to multiply our carbon compound by 6. That doesn't mean that we can just answer 6 though, because we have to make sure everything else is balanced first. And now you see what happens down here with our oxygens. Because we're multiplying this carbon by 6, we're going to multiply specifically the number 2 by 6 as well. So now we have 12 oxygens from the CO2 and 1 oxygen from our H2O. So we have 13 total now. That'll change again in a minute when we adjust this coefficient, but that's how we're going to keep track. we have 12 oxygens here, or 12 hydrogens here rather, and we have 2 hydrogens here. So we'll want to multiply this by 6 as well. So we'll put a 6 in front here. So we're going to be multiplying this oxygen by 6 as well. And so now when we add these two together, we've got 18 oxygens total. All right. So now we come back over here. What number do we have to multiply by 2 to get 18? We're going to have to multiply that 2 by 9. Now that we see that everything's balanced on both sides, now we can feel confident saying that yes, 6 is the number that's in front of my carbon dioxide. So my answer choice here is going to be C. We have 6 CO2s. Okay. The question or the equation for number 29, they're asking us a similar type question. They're giving us a reaction and they're asking us specifically for the coefficient that belongs in front of the potassium hydroxide. So the equation that they give us looks like this. This is our potassium hydroxide, so we'll underline it. We see in this equation that our polyatomic ions have stayed intact on both sides of the reaction. So we're going to be able to keep them together when we take account of our atoms here. So we can count our aluminums, we can count our sulfates as a unit, we can count our potassiums, and we can count our hydroxides as a unit. Okay, and we have 2 aluminums, 3 sulfates, 1 potassium, 1 hydroxide. We have 1 aluminum, we have 3 hydroxides, 2 potassiums, and 1 sulfate. Okay, everything is a compound in this case, so it is perfectly fine to start out anywhere you want, really. So I'm just going to start out by taking my aluminum and multiplying it. We've got 2 here, so I'll just multiply my aluminum compound on the product side by 2 to make those the same. So I'm going to take that 2 and put it in front of my AlOH3, which means I'm also going to be multiplying my hydroxide number by 2 as well. Okay. I've got 1 hydroxide here. I've got 6 hydroxides here, so I can multiply my hydroxide compound by 6, which means I'm multiplying the potassium and the hydroxide by 6. Come back over here. If I have 6 potassiums here and I have 2 potassiums here, I'm going to have to multiply my potassium compound by 3 to get 6 potassiums. So I'm going to put that 3 out in front here. So it's going to apply to my potassium and my sulfate. And now I see I've got 2, 2, 3, 3, 6, 6, 6, 6. So everything's balanced. They wanted the coefficient in front of my potassium hydroxide. And that's going to be 6 in front of my KOH. That's going to be answer choice E for that one. Okay. All right. The next question, which is the last one we'll do in this part of the video before we break it up. Let me share the screen. It says, my little pen here. What is a possible mole to mole ratio for the following balanced equation for the combustion of methane? And this one is asking us, like, which mole ratios make sense based on what you're seeing here. Remember that mole ratios involve the coefficients for your balanced equation. Okay. So every 1 mole of CH4 is going to react with 2 moles of O2. So we can kind of go one by one and check these out. Let's look at the H2O and CO2 relationship for our next one. So 2 moles of H2O react, or 2 moles of H2O are produced along with 1 mole of CO2. Right? It's not 1 to 1, it's 2 to 1. So this one's no good. All right, let's look at our next one. This one's asking us to look at, oh, it's still moles of H2O, moles of CO2. So this one looks better. So this is, part C says 2 moles of H2O for every 1 mole of CO2. That one looks good. Choice D says 2 moles of CH4 for every 2 moles of O2. Nope. And then choice E says 1 mole of CH4 for every 1 mole of H2O, and that one's no good either. Okay. So the only one there that makes sense in terms of our mole ratios for that one is going to be choice C. Okay. So that'll be the first half of this video, and we'll come back with the second half a little bit later.